r greater than 0 such that the open ball around the point x with radius r is fully contained inside U. And this is true for all x. Then it's open. What is closed? Its complement is open. So, example in R, any open interval is open and closed intervals are closed. And in Rn, the notion essentially extends in open intervals cross products are open in Rn and closed intervals cross products are closed in Rn. And you, instead of considering balls, you can technically consider open rectangles or cubes in Rn, and do, instead of ball definition, you can give a rectangle definition. You say that if there exists a rectangle around the square, around the point that is fully contained, then the set U is open. Anyways, so we'll start. Essentially, first we'll do some notational thing. Introduction to notations. C infinity. So first of all, assume omega is a subset of Rn and open. Then C infinity of omega is the set of all functions f from omega to r such that f is smooth. What does smooth mean? All derivatives exist. Now, technically speaking, you are now differentiating with respect to n coordinates. So, then I'll also put this in notation. If alpha, so alpha is equal to some alpha 1, alpha 2, alpha n. This is called a multi-index if alpha n belongs to natural numbers. Now, when I say natural numbers, I include 0 as well. And d alpha of f is to say the derivatives with respect to alpha ith coordinate. So, the derivative of order alpha I for the ith coordinate. Essentially to say, if you denote the coordinates of omega as or Rn as or x1, x2, x3, xn, then d alpha of f is essentially derivative with respect to x1 to the power alpha 1 or alpha 1th derivative with respect to xi, and then derivative with respect to x2 alpha 2 times all the way up to for all coordinates. This is well defined in any order of these because, well, f is smooth. So this is multi-index notation. I do not think there are other notations. There is one more. Support of f is to say set of all x belonging to omega such that f of x is not equal to 0. And you say closure, so rather I'll define the complement of it. I anyways need to define closure. So closure of this. Now, to say what closure is, you say C closure to be the set C union. What are those called? Limit point. Yeah, limit point, sure. Cluster points as I prefer, but limit set or limit points of C. And everyone is fine with limit point definition because I heard you guys also say that. Or should I define what a limit point is? You want?
I don't.
Okay, so x belonging to x is said to be belonging to limit set of C if for all, now because we are in Rn, I will just work with open balls. For all balls centered around x, B intersection C first of all non-empty and non-singleton. Why I say non-singleton? I don't want isolated points also. Because if it's isolated point, I can take any ball around it of some small enough radius, and the intersection will be singleton. So it doesn't give me a feel of limit point. I want to feel a limit point, so I define it like this. So closure is defined as this. Essentially to say, if let's say our function is something like this, bumpy function, it's literally bump function. The closure of the support of this will be this set. Now when I say not equal to 0, it will be an open set, right? It goes to 0, but I don't take the 0 wala point. So now it's an open set. So to get a closed set, I take the closure and you get the set this. We will formalize what a bump function is as well. We will require this in our today's session. We will not be erasing this part of the board, but I need to define one more. So I'll define it here. C infinity of omega is essentially set of, so it's essentially set of all functions from C infinity of omega such that the support of f is compact. What does compact mean? Sure. So it's a closed set that is bounded in Rn. Not always true, that is why.
Finite subcover.
Yeah, finite subcover. But let's not go to cover definition. That's why essentially, because we are dealing with Rn, it's a bounded closed set in Rn. Hence compact. So yeah, another special function we'll be dealing with a lot today. So because these things are obvious, I will just remove this. These parts are obvious, right? These ones. Or do I need to write them again? Yes. So I will define my bump function around x as, so this is because it's in Rn, exponential of 1 divided by 1 minus mod x square. I mean, I don't need square, but I want smoothness. So mod x square. This is how I define my bump function. Now, well, one more thing, this and 0. So this is if x is less, mod x is less than or equal to 1, and this is if mod x is greater than 1. Can you tell me why this is smooth? Or a better question, is it smooth?
Is it minus or plus?
This one?
Yeah.
Minus.
It looks like this.
It looks like this, right? No, I don't want it to go like this. I want it to go like this.
Yeah, I'm getting this.
Shall we?
Mod x equal to 1 is not even
Yeah.
defined.
Not even defined.
It's minus at the top.
Ah, sure. Okay. Minus 1.
Open minus.
Yeah. My bad. Oh. Rookie mistakes. So yeah, just because I wanted to tie it down. So essentially, first try to see how it looks like. Best case, take it in R. So now essentially my x is just between minus 1 and 1. So it looks like the bump function I made there. It's also called a pimple function. It's not made by me. It's literally called the pimple function. And well, there are special functions called mollifiers, which is essentially something derived from this. This is denoted as, this is rho of x by epsilon. And yeah, that's it. And I think there is some factor as well, some c times rho as well. Now because this is a bounded function and its support is compact, I can integrate this and it will have some finite value. Take it as an exercise and see that the integral is 1 of this function. So because the integral of this function is 1, the integral of this function for every epsilon is also 1 without this constant. Right? So, well, I can just divide by that integral value, c, so that this function also has integral 1. Right? So that is why I don't specifically remember what the value of this was. I think it will be some 1 over epsilon to the power n some 2 pi something. So that is why you divide by that. So that is why it's c epsilon times rho x by epsilon, so that the integral of this is 1. That's it. And that will be all the notations required. And we can start. So essentially you have seen things like these, right? So if I have a function f which is continuous, let's say, because I defined c0, I can also define c, so it's just continuous. Never mind. So continuous function on omega, then I can define this thing, integral f times any function from this c infinity this is, I say that this is well defined. Any reason as to why?
It's 5. Mod is 5. 5 is a bumper.
No.
Ah.
Can you tell me a reason as to why this is well defined now? Not before now. Essentially because the support of this is finite. You wanna see why? Essentially, if you take mod of it, this is bounded by the highest value f can take, or rather remove the highest value f can take. This function, because it's outside the support of phi, this integral will be 0 because phi is 0. True? What does this thing mean? C infinity means f that is smooth such that the support of f is compact. So the support of f is, let's say in R, it's a closed interval, let's say. Outside of this closed interval, everything is 0. Right? So outside of this closed interval, the function takes value 0. So the interval also has finite length now because I said it's bounded because it's compact. So this integral essentially is now integral over, let's say, some closed interval, or in Rn it will be some closed set that is bounded. Let's say it's M f phi dx, and now phi is a because it's smooth, it's a continuous function in a bounded set. So it will have a supremum that is well defined. It will be not blow up. So now I can take this out. So I write supremum of f, let's say, by this thing. This is the supremum of phi, and this will be just integral of f over m. And now this is finite because, well, it's the Riemann integral of f on a bounded set, and hence this is well defined. Now there are simple things to check, like this operator. If I take
Vivek, what is that?
this thing,
Yes.
it's the supremum of phi over Rn.
Okay, wait. So that entire thing is greater than whatever.
What entire?
What have you written there?
This thing is greater than, or this thing is less than or equal to this. Yeah. Fine. Yeah. So this is well defined because the mod of this is finite. That's it. It doesn't blow up. So this thing, can I say that this is a linear function on this thing? Take two elements from here, you add them up, addition is well defined, and because integral has this nice property that's it's linear, you can essentially go by term by term. So that is why it's a well defined linear function. Now essentially what distribution theory concerns with is, and also this is also called the set of test functions. The reason as to why these are called test function comes to something called weak differentiability, that if we have time we'll see it afterwards, but nonetheless these are called set of test functions as well, and we want to put some kind of in language of topology, give some topology to this thing so that these functions become continuous as well. These are linear, but we want to make it continuous. So the set of all such continuous functions, I will give a topology for the topology guys, but just in the layman language, the set of all linear functions, I will give a notation to this, the set of all linear functions from Cc infinity of omega to R, because this was a function to R, it could be C, I mean in general it could be C, and such that T is linear and continuous. This is denoted as d dash of omega. Now why d dash and not d of omega? Because in literature Cc infinity of omega is denoted d of omega. So that's why. Anyway, so this set is in fact called the set of all distributions. So T is said to be distribution if this is true. Now the main term here to specifically follow is, what does continuity even mean here? Everyone knows continuity in Rn. You use epsilon delta definition. What does continuity mean when we are in a set like this? This is not Rn. This is in fact an infinite dimensional set, infinite dimensional space. So what do you mean by continuity here? So whenever continuity is said, you technically require something called topology. But instead of directly going into the topology, I'll first define a continuity for this. So I say a sequence Fn subset of Cc infinity of omega goes to 0, that is Fn goes to 0 if I have to write everything. So if d alpha f, well, first of all, there exists a compact set K such that support of Fn, all of these Fn's are inside this compact set, and all the derivatives of f go to 0 pointwise. Now it will be uniform as well, but the reason as to why is because, well, all the supports are contained inside K. So, well, this is how I define how Fn goes to 0 in Cc infinity. So a visual way to see this is, if you take, let's say, bump functions, and the bump functions are kind of like reducing in size, like they're going to 0 like this, then that is a function that follows this. Because what would be derivative of a bump function? Anyone can answer, by the way.
E raised to whatever.
Huh?
Whatever that stupid thing.
It looks like another bump function. It's not exactly a bump function, but it looks like another bump function, because it will be 0 here, and now because the derivatives are defined anyways in this region, wherever it's non-zero, it will have to go some squiggly line like this, and then has to go 0 again. So it will be some weird kind of bump function, but it will still have a compact support, and hence, as my size decreases, all of these values have also go to 0. Now, obviously when I say all of these values, the bump function peak also I am taking to 0. So essentially all of these uniformly go to 0 on K, along with all its derivatives. So that is why, that is one example, and well, other examples you can make on your own artificially.
What is F?
F? Fn.
Yeah.
Fn. Yeah. So this is how I define continuity or sequential limit in Cc infinity. Now how this induces a topology for the topology guys is, you define what is called semi-norm with respect to derivatives up to order n, and you bound them by 1 by n, and take them as local basis. Figure it out. Anyways, so with respect to this, I say now I'm not going into the topology because topology might be a bit too much for this session. That is why we'll just define the how when a distribution belongs to this using this. So T is said to be a distribution. So as in to say T belongs to D prime omega if for all Fn such that Fn goes to 0 according to that limit, T of Fn goes to 0 as well. In R, because T of Fn is in R. So can you give me an example of T? Now. Anyone?
0.
I'm not that trivial of an example. So yeah, 0 distribution obviously.
Just a constant.
Just a constant, sure. I mean, constant.
Integral.
Constant integral? Is it?
Integrate a form function. Form function is your sample of fn. And you can integrate it and.
I mean, sure. So, I mean, a constant function does define. So, any constant function times this also follows. Other than that, so as I said, if f is any continuous function,
I think so.
then I'll denote tf operator as integral f dot. So dot instead of dot, you will replace it by the function you are operating it on. So these are also functions that belong to a distribution. As to why? Because well, first it's linear. Not close and bounded, but you essentially have to see if this is followed. So essentially you have to see now f and fn's and g here. So if you take g and fn, you need to see if this goes to 0. Someone tell me why it goes to 0.
What is that?
G is a continuous function.
From where to where?
From Rn to R. That's it. Rn to R.
One thing I had to ask. CC infinity is a non-linear space, right?
It's a non-linear space. What now?
And just take the supremum of F. You
Sure.
can't take it.
I'm not taking.
So this
Topology.
topology is different from
This
that.
topology is different.
Okay.
This is induced by something called semi-norm over n. So semi-norm with respect to a
And they're
natural
not-
number n.
They're not equivalent.
They're not equal. In fact, you can make the supremum norm using those norms. So that's a very strong topology. That is why
Oh.
if you see this,
Uh-huh.
these also kind of belong to our usual dual space as well.
Mhm.
But
Yeah.
now I will show you that there are more elements.
More element. Okay.
So it's a weaker topology. That's all. Anyways, let's not go there. So this goes to 0 as to why?
The same reason you showed that it's bounded. It's the support.
That was to say that it is well defined. Now I have to show that this sequence of numbers go to 0.
Because G is on finite support as well.
G does not have finite support. G is just a continuous function.
Oh.
Fn's have finite support, and remember this.
Fn goes to 0.
Derivatives go to 0 as well, but all of these guys have a fixed support, fixed compact set inside which they have the support. This is a very important thing because during my presentations and all as well, I kind of got confused on this part and got one of the results wrong. But we clarified that afterwards. We were about to disprove a theorem and then we were like, okay, it was just my mistake. So anyways, this part is important. So this is because for one, because of this thing inside K,
Support of Fn would shrink, right?
huh?
Support of Fn would be smaller.
Support of Fn goes smaller, and because Fn goes to 0, the mod Fn is bounded. Mod Fn is bounded, fine. So integral g fn is less than or equal to mod fn times integral over the compact set K and G. This goes to 0 point wise, because this is a stronger criteria, and from the stronger criteria that is also implied, which is a weaker power. So this goes to 0. Hence these guys are distributions. Now there is another thing. Are these the only thing that define distributions? Well, no. Now specifically I have been taking continuous functions, but you can take something called locally integrable functions, which have to say integral of f. So now I'm not taking continuity as well. These are just Riemann integrable functions, let's say. In general you say Lebesgue integrable, but just Riemann integrable is works. So Riemann integrable functions such that over any compact set K, this has finite values. Then f is said to be locally integrable. Anyone has any doubt about what a locally integrable function is? Anyone? No one? Yeah. So any continuous function is a locally integrable function, because over any compact set it's bounded, and well, you can take the bound out, and any compact set integral is well bounded, because well it's just, let's say, the measure, essentially volume of the set, and volume of any bounded set is bounded. So hence a set of all such locally integrable functions is defined as L log. So because we are taking over omega, I'll take omega, but instead I can take Rn. So TF again also defines a distribution, because again when I go here the same thing is applied, but now I do the same thing and Fn comes out, mod Fn comes out, and mod Fn is bounded, so again it goes to 0. So TF again belongs to d dash omega. Again, are these limited? No. If you consider, okay, so to the people who are familiar with measure theory, any borel, complex borel measure on Rn also defines a distribution on this set, essentially by this. So T mu I will denote, T mu of phi is defined to be just the integral over Rn of phi d mu. This also defines distribution on a distribution, because well, first of all it's linear, obviously, and second, well, it follows that you can apply dominated controls. Do not care about that. It's just to say that there are other elements. Now again, are these limited to this? No. It's a very big set is what I'm getting. You can, so there is another distribution which was kind of the main thing I was hinting on. Delta of f, or I will stay consistent with my notation. So delta of phi is defined as phi evaluated at 0. That's it. This is how I define delta of phi. This is in fact your Dirac-Delta distribution, as they would say, not the function. Dirac-Delta distribution, and reason as to why this is now so simple. You take a sequence. What is delta of Fn? It's just Fn of 0. Fn of 0 obviously goes to 0, because Fn goes to 0 in a very strong condition, pointwise. So delta function or Dirac-Delta distribution also belongs to this thing. Now there is a nice way to see, or it's a nice thing that you can try to prove that there exists no f for which T of f is delta. A small reason can you give me? Anyone there? Or here as well, if you guys have an idea. So this is an important part.
T of
Delta
Fn.
0 will be infinity, so it won't really be better.
Delta of 0 is infinity.
Like the Dirac-Delta function. Like delta function, if you put f as the Dirac-Delta function.
You can't put f as a Dirac-Delta function.
Then
What is a delta function?
0 everywhere except when 0.
Is it a well-defined function?
It's not a
It's not a function. And also it doesn't belong to C infinity. Yeah. So so essentially the theorem that we'll now go for, I will do it two ways, or rather I will just do it one way. This part you will be able to figure out on your own. It's easy. So essentially my theorem is there exists no f such that when I say f is locally integrable, and this is the largest set outside of which it just becomes bad. So that is why we restrict ourselves to this set such that t of f equals delta. So well, for one we need to see why not. So take fn's. Wait. Now take fn such that fn goes to 0 and you evaluate t of f. T of fn. Tf. Okay, I need to be consistent. Take phi n going to 0 and take tf of phi n. Now because phi n is always inside a compact set, essentially to say, or rather I can do one thing. Yeah, right. I take phi n specific thing now. So support of phi n is inside -1 and 1. Let me take close. And I take phi n going to 0. Now you take t f of phi n, which is to say phi n of 0, or so essentially assuming this is true, this is not true, there exists an f. So this is essentially phi n of 0, and this would be equal to the integral of phi n f over r, or rather because the support is anyways inside this set, -1 to 1. What I do is I take phi n divided by this value. So I define my sequence psi n to be phi n divided by t f of phi n. That's it. Now this is well defined because, well, this is just a scalar and you are dividing it by a function. That's it. So now because phi n goes to 0, psi n also goes to 0. This is independent of any variable. So psi n goes to 0. So you essentially get this part. Again you apply tf. So you get psi n of at 0. But what is psi n of 0? It is essentially tf of psi n divided by tf of psi n. Huh? 1. It's equal to 1. But psi n goes to 0. So as n goes to infinity, psi n of 0 is equal to 1. But this is equal to delta of psi n, which technically should have also gone to 0 by the definition of distributions. Right? Hence, there exists no f. Everyone convinced with this argument? So that is why this is to say that there exists no function f such that you can represent delta function as t of that function. So this is, well, for one, this is to say that the set of distributions is pretty large. There are a lot more stuff than you think other than just t of that. So essentially when you come to measure theory course, you will define something called LP spaces, and when you say the linear bounded linear functions, like functions like these, linear functions on LP spaces, you get another LQ space. So there, essentially, your linear functions are of these form. So the point I'm getting at is, when you say take dual of this, it's in fact bigger than any LP space. So that's it is to say it's a very big space. Now we will also prove in this session that in fact using all these theory, this is dense inside. Dense, now I don't think you will get what dense is, or I don't know if you will get what dense is, but for everyone who gets it, this set is also dense inside LP for any P. So, well, even though LP dual is some LQ, the dual of this is even bigger with respect to this topology per se. So these are essentially what distributions. The reason as to why we study them is to define a lot of things in math. Something like you might have seen. How many of you guys have seen Green's function? Huh? Heard of. Everyone else, I suppose. So.
Actually, I'm
So you don't remember what a Green's function? तूने ODE course लिया था. So.
there was a green.
Yeah.
Oh,
So.
I don't know actually.
So for general linear PDEs, in general PDEs, what are PDEs? It's essentially differential equation. I am a partial differential equation. So I'm pretty sure what a differential equation is familiar with everyone. So assume I get some linear PDE with constant coefficients, let's say, just to make our lives easy. AI R D alpha f is equal to, and now I have to take alpha, so alpha exists is equal to some function g. To solve this, there is one thing that I think you guys might have seen. You solve this first, d alpha of some function p equals delta. As I said, the concept of a delta function is pretty stupid. I mean, it's not well defined at all. So this thing itself doesn't make sense. What do you mean by derivative being a delta function at a point? So that is why this is a very stupid concept. But the reason why this even is, this remotely gives us a valid answer afterwards, is actually well developed through distribution theory. In fact, the whole concept of distribution theory was made to formalize this concept. But the surprising fact is, before this concept was made, Dirac independently somehow came up with Dirac-Delta function without applying distribution theory. Though if he did, there would be much finer results which were found afterwards. So essentially, this one equation is the reason why the whole concept of distribution theory was even made. But afterwards, it found its applications in various fields such as harmonic analysis, if you know what it is. And why harmonic analysis is pretty useful is a very wide thing. But one of the applications I know is analysis of central limit theorems. Everyone I think has heard of. Analysis of central limit theorems in spaces where you define sequences or sequences which terminate. These are called uniform something sequences, and there you want to see how the sequences are, in space, lying in the space. So there you want to see how central limit theorem applies, and harmonic analysis is used somewhat in that area. And in harmonic analysis, you have some studies where you use distribution theory. Tangents. Anyways, so we'll come back to our basic distribution theory now. What should I do after this? There is a lot of things I can go from here, so let's see. We can do another thing. We'll define something called support of a distribution now. Now, how did we define support before? Support was defined as wherever function doesn't take value 0. How can you say, what can you tell about support of a distribution for any of the guys here? How will you define support of a distribution?
You can give a topology on C infinity omega and you can define support.
Without topology or anything, just with, don't consider this closure, just as a set. How would you say it?
A set of all smooth functions which gives you, which doesn't give you zero.
Exactly. So when you say support without this closure part, now I won't consider the closure part because I don't want to go into the topology of what that set that we have defined there. But without this closure part, in the set language, you will just say set of all functions there such that t of the function is not 0. Now it's a very nice definition. No one has a problem with this. The only thing is it's useless per se. That is why you want to define some kind of support of the distribution in omega. This is a very weird concept if you are familiar with how things work in math, because well, the distribution is a function from c infinity of omega to r. But we want to define support of t. Now, when I say support, I will keep it with a capital letter now, just for the sake of it. Now I want to define it in omega, which doesn't make sense right now, right? Because it's a function from this and not from omega. So that is why we have to give a definition for what this is. But it will be a useful definition. The reason as to why is, first we will see where t vanishes. How do you define when t vanishes on a set? So if you, for that we will first define restriction. If you consider, okay, just for the sake of language, I will define d of omega as cc infinity omega, because I don't want to write all these letters again and again. And d prime will denote the respective distribution space. Comfortable, everyone? Yeah. So if I take, let's say, a distribution t belonging to d omega naught, where omega naught is a subset of omega, or rather if I take this thing and then take omega naught subset of omega, can you tell me if t is also a distribution is in d of omega naught? I want to create some function t prime such that it belongs to d prime of omega naught. This is my aim. Can you tell me how you would construct this?
All functions continuous on omega are also continuous on
Omega naught?
on omega naught. Those omega
It's,
naught.
sure, but that is functions here. But that is function on d or d of omega naught. You are close to the answer, but you are not. You're just one reasoning away from the answer. His point is, if you take phi belonging to d of omega naught, it is to say its support belongs to omega naught, and it's compact. So you can define omega tilde belonging to d omega as just an extension of this function to this onto omega by saying that okay, it's 0 everywhere else outside omega naught. Do you see the reason why? If you restrict it to omega naught, omega tilde is omega. Sorry, phi tilde is phi. And if you go anywhere outside omega naught, it is 0 completely. So it's a well-defined extension. So I can define t tilde of, let's say, some function phi. Phi belongs to d prime omega naught, d omega naught. This as t of phi tilde. This is what I denote as t restricted to omega naught. Now I define it. So you take any function from the smaller set, any function smooth on the smaller set, you extend it outside by taking it 0. You take the evaluation with respect to the distribution, and that is what I define as t prime on the original function. This is called a restriction map. It will be pretty, and now you will probably be giving me, you'll probably be swearing in your head to me as to say that this is an obvious definition. Thing is, it's not obvious at all. Restriction maps are something that are not always, like, it's not necessary that it is always followed in math. So you need to go through as to say, okay, is this well defined or not? It's just, in our case, it's a pretty nicely following definition. That is why it follows very nicely. But in general, restriction maps need not be nice. So that is why I stressed on the argument. So if you have a distribution on a bigger set, when I say omega, you can define distributions on smaller sets using restriction maps. So yeah. Now we can define support or vanishing set first. So I say, this is a different definition. T vanishes on omega naught subset of omega if t restricted to omega naught is 0. As to say, for any function that belongs to, that is smooth on omega naught, the distribution takes value 0. An example is, take Dirac-Delta. Any function, if you take the smooth functions on r minus 0, if you take smooth functions on r minus 0, that delta on that will give you every 0 any time. Because what is delta? It gives your valuation at 0. Right? So that is why this is how we define it. So, well, once we have vanishing set, hence we can also define, what is it called? The support now. What is support? What? Well, a bit more. I want the support to be closed. Whenever we say support in math, I want it to be closed. And because it's an omega, I can talk about closure. Before I was not talking about closure because I didn't know what a topology on this thing is. They might, but in general, the definition of topology might be a bit too much for you. That's why, rather than considering any closure there, I was just considering a set. But now that I am in omega, I can say what a closed set is. So, support of T, a distribution, is complement of the largest open vanishing set. This is how it's defined.
So, if I take, let's say this usual bump function.
Usual what? Bump function.
Yeah.
Huh.
And I take delta as my distribution.
Sure.
Then, and I take r minus 0 as to be my omega naught.
Yeah.
And the way you extend it to phi tilde,
My phi doesn't belong to this thing, right?
my phi,
So if you take bump function,
right?
bump function restricted, so bump function does not belong to this set unless, because it has to vanish, right?
No, bump function Why?
So,
I mean,
okay.
I take my omega to be r.
Uh-huh.
Right. So my bomb function belongs to d of.
You said r minus 0, right?
No. Firstly,
R,
I take
R,
it
R.
R. So my bomb function belongs to d of r.
Huh.
Right. Now I take omega naught to be r minus 0.
Huh.
And I want to take the restriction of the delta distribution.
Huh.
Then its value on.
So now the thing I told you, right?
Oh.
You have to go
Sorry.
from smaller set to bigger set.
Okay.
So I'll
I need
explain
to go
his
down,
example and why he was then getting confused. If I take bump functions, bump function belongs to d of r, let's say. So I'll take r for better visualization. Fine with everyone? His argument was, if I take delta distribution restricted to d of r minus 0 and operate it on rho, extension, this should give me rho of 0 which is equal to 1. I am saying this is wrong because rho does not belong to d of r minus 0. If it did, its support must be compact and sitting inside r minus 0. But its support is minus 1 to 1, and because you remove 0, it's removing 0. But that is an open set in R. So it's not compact for sure in the restricted topology as well. That is why this is not true. This is not a restriction map. And well, this is nonsense because you can't operate it on rho. This by definition is defined on d of this thing, and this thing does not belong to this set. So this is nonsense. So yeah, this is how I define complement. Now this is a very abstract way of defining this thing. So a very useful way of seeing this is take TFs. So whenever you are working with distribution theory, you always try to see how definitions are with your nice functions like f, TF, distributions generated by functions. So if you take f, let's say with compact support, f has compact support, k. What is, let's say, the support of TF? So I take essentially analyze how this integral works. So because the support of f is restricted to k, this is obvious, times phi. Best way to see this, where does it take value 0? Where is this integral always 0? Like the simplest scenario.
Outside this?
Huh?
No.
Where is this integral 0 for any phi?
Huh.
Wherever f is 0.
Wherever f is 0 is a trivial scenario, but like for what phi's can I say this integral is 0?
If the compact
Support.
is outside whatever k.
Exactly. If the support of phi is outside k, this integral is always 0. Right? So you can at least say that this is true. Support of f. This is at least true. Fine? Other way around, well, you go by the same argument. It's an if and only if argument, technically speaking. So that is why you get this equality in fact. So if your function is compact, or forget about even compact. I took compact because, well, it is easy to see. But in general, even if I did not have compact here, it was just a set k. Let's say the support of f is just a set k. If your support of phi was outside of k, this integral will be 0 because the function will be taking value 0 here inside k. So this integral is 0. So again you have one way around, and because it's an if and only if condition, you get equal to. So for any function, for functions that generate distributions, these are called distributions generated by f, the support of TF is essentially same as support of f. It's just when you come to abstract distributions like Dirac-Delta or something like with respect to measures. So for measures you get measure zero sets, as they say, or union of those measure zero sets. So
These f's are all the integrable f's, right? Any generator f, not necessarily one of the continuous ones.
any locally integrable.
Any local.
Also, when I said locally integrable, technically speaking, it was mod f. It was not just f. Now, given that if it was f, you can also say mod f. But in the definition, at least, it's always mod f rather than f. Yeah. So this is essentially how I define support of T. Now there are nice things that you can do now with this, or rather restriction maps in general. You can define what are called partition of unity with distributions. I wouldn't go there because now it's a real analysis concept, or rather I would say measure theory. It's a concept, I would say. But anyways, you can put partition of unity, locally finite partition of unity, restrict it, you get locally finite distributions. Locally finite partition of unity distributions. That's it. It's as simple as that. And now it is well defined because take any phi, it has a compact set, it will only intersect with finitely many of the open sets, and hence the sum becomes finite. So it makes sense. Now as to why I said this, it's a pretty useful concept when you're analyzing this support in more detail afterwards. But we will not go there, that's a different concept. So now we have things that are nice with these. Now as the name suggests, these are test functions. In general, we need C infinity functions. So for C infinity, we analyze the same thing. Why did I write that? So we want to, okay, I will define C, so another notation for this because I don't want to denote infinity again. E of omega. That's it. I want to see or define distributions of some form on E of omega. So well, that I can define in a similar way using first I have to take the limit condition. So here I took limit of sequences. I need to first define sequences here as well. So the limit of sequence I defined here as fn goes to 0 in E of omega if now I will not write this whole thing, but okay, I will write it. For all compact set K, d alpha of f goes to 0 uniformly on K. So for any compact set, the derivatives, all the derivatives go to 0 uniformly. This is how I define sequence limit in C infinity, smooth functions in general. This is different from back there with one key thing that you have to see, that there was this thing key support of all fn's has to be inside one specific compact set. Now you don't have that condition. In fact, you can't say that condition because fn in fact need not have a compact support. Example, take x square. It doesn't have a compact support on R. So yeah, its support is in fact R. So not supposed to say that. So yeah, for sure you see that now I can't apply all the distributions because if I take, let's say, locally integrable functions, the integral will be on R now. Let's say if I take omega in R or omega equal to R, the integral will be on R now. So this integral, now because for simplicity's sake, let's take f to be uniformly equal to 1. This of course belongs to E of R. Take any derivative with 0. Right? And let's say g is a locally integrable function. When I say locally integrable, you can take x square. X square is a locally integrable function. On any compact set, it gives you integral finite. If you take Tg of f, this will be integral of x square on R. no longer well defined. It is infinity, if you have to say something about it. So this is now no longer well defined. So you know for sure that the set of all continuous distributions, the set of all distributions now is at least, not all of them apply here. That is for sure. But you want to see what all apply. Now there is a very nice thing that you see, this is technically speaking a linear algebra concept, that for those people, if you take V, vector space V, which is inside vector space W, set of all linear functions which are continuous follows this. The subset relation kind of reverses. So that is why it will be an easier concept to deal with in this case as well. So you will for sure, so in the sense, this thing kind of has a direct injection here with the preserved topology. Topology I don't speak here, but the topology you can see that it actually gets preserved. So it has a direct injection here. Any set there is smooth, any function there is smooth, so it also here, it is also here, not the other way around. So you for sure know that this thing is true. This is true. But
D prime.
D prime. So D of omega was our CC infinity. D prime is the set of distributions.
No, because you use the prime there.
This is also same.
It's the same thing.
It's the same thing. This is called dual spaces, by the way. These are all set of linear functions. Again, linear functions.
Okay.
Yeah. So you know this is true, but now you want to see concretely what all functions actually belong here. So now there is one way to say it. Suppose you take, for an example, you take delta. Does delta belong here? Anyone?
Sure.
It does. What is sure? I'm not just sure, man. Just get included. Yeah. So delta belongs here because if you take valuation, that is delta of f of x, you get f of 0. So if you take fn, this going to 0 implies pointwise again. So fn of 0 also goes to 0. So delta for sure belongs to E prime. So well, this is a set with compact. It's a distribution with compact support, right? Its support is 0, literally singleton 0. So now what I see is, okay, I see this. I take a function f with compact support. This integral again makes sense. G, where G belongs to E. This integral makes sense because this is bounded by, this is well bounded by, first I'll take equal to, this is equal to integral over the support of f. So support of f, which is compact, and then I take fg. Now because of the fact that g is continuous, because it's smooth, g is continuous and it's over a compact set, I can take supremum and you get supremum of this, and then you have integral kf, which is again a finite value. This is well defined. So you for sure know that if f has compact support, if f has compact support, Tf also belongs to E prime. So now I at least get this weird thing ki, oh shit, compact support distributions seem to be belonging to E prime. So I try to prove that the only elements that belong to E prime are in fact distributions with compact support. So theorem is, if T belongs to E prime, support of T is compact. It's actually quite an easy proof. You first kind of do this. So you take omega, or instead of omega, just consider omega to be Rn right now because it's easier to see, and well, you can restrict it to omega. It's an easy proof, that's all. So take omega to be Rn, and what I'll do is I'll cover Rn using open sets, increasing compact sets. So I take the balls of the radius 0, n, natural number 0, n, and the closed balls. And because for as n goes by natural numbers, the union of these guys essentially cover Rn. True. So I partition Rn using this, and I essentially go like, okay, assume my theorem is wrong and the support is in fact not compact. So this is as to say, I go via saying that, okay, let's suppose there are phi n's such that support of phi n is contained inside ball minus, so Rn minus the ball of 0, n. This is how I define phi n's. You can do this because of a concept called partition of unity, but in general you can see this as to say it's a kind of like a wave. So you take the ball, 0 in the ball, you take a bump function that goes like in a circular way, and it kind of looks like a wave in the water. That's it. And for anyone who is familiar with partition of unity, this is always doable because of partition of unity. And well, such that. So now you can obviously see that phi n goes to 0, because as my balls increase in size, it is 0 inside. Any compact set sits inside one of these balls, big enough ball, because compact sets are, as he said, bounded and closed. So there exists a big enough ball inside which the support of phi n kind of sits, or rather any compact set sits. And what was my definition here? Phi n goes to 0 if any derivative goes to 0 inside any compact set. And for big enough compact set, phi n are completely 0. So that is why phi n goes to 0 in E of omega, or E of Rn in this case. So we for sure know that T of phi n should go to 0. Fine. Now, well, I take T of phi n, and because of the fact that I assumed it's not compact, so if you know what, so support is a closed set, right? Support is closed set, and I'm saying it's not compact. So I can also choose phi n such that T of phi n is not equal to 0. T of phi n not equal to 0 and support of phi n is inside this condition and this condition. This is for existence of phi n, and this I can choose because I have taken the assumption that the support is not compact. So it's an infinite set. Support is a closed set. If it was bounded, then it's compact. So it's not bounded is what I am assuming. Because it's not bounded, there exists phi n such that T of phi n is not 0. There exists phi n such that T of phi n is not 0. So essentially my way is I divide phi n by T of phi n. So I take psi n to be equal to phi n divided by T of phi n. Again you do the same thing, you get T of psi n's to be equal to 1 for all n. But well, if phi n goes to 0, psi n should also go to 0. But that doesn't happen. So contradiction. Anyone has any doubt with this proof? You seem confused.
What is it that you're trying to prove?
I am trying to prove that if T belongs to E prime, then T has compact support. I assume not. So the support has to be an infinite set.
Yeah.
So there always exists phi n such that it has support inside of the complement of balls, and it is T of phi n is not 0, because that's my assumption. If it was 0, then it has compact support.
Okay.
Yeah. So hence contradiction. Any doubts? Yeah. So essentially that's how I proved that. Okay. So it's a nice thing that if T belongs to E prime, T has a compact support. So essentially E prime is just a set of all distributions with compact support. That's it. There is nothing else that is special. It's just F belonging to T belonging to C prime of omega such that support of T is compact. And this is in fact the reason as to why we came here is, you remember how in physics classes they're like, okay, Dirac-Delta function is, we can approximate it using Gaussians, right? We will see as to reason why that can be done. For that, we will need another concept for convolution. There are more concepts by the way here. There are something called constant rank theorem, first order theorems and all, which essentially say how distributions kind of have a good bound on compact sets. So for people who have done functional analysis, you have linear bounded operators. So why they are continuous is because they are bounded, right? There is something that is similar to a bound here, but the bound changes with compact sets. So yeah, that is there. And because of the fact that if the support of T is compact, you're essentially dealing with a compact set, it actually in fact becomes a bounded linear operator. With respect to some semi-norm, of course, but it actually acts like a bounded linear operator. So there are many theorems that follow that, but we will not do that. We essentially want to get into how to solve this Dirac-Delta, or first at least formalize what Dirac-Delta is. So we formalize that, but we want to also see why the Gaussians kind of go like that. Because if you go with the usual definition, that it is 0 everywhere and and infinity at 0, and go by the Gaussians, I can multiply the Gaussians by any scalar, still take the limit, still 0 everywhere and still infinity. First of all, the definition does not make sense for the Dirac-Delta, and second, the limit does not make sense because it's not unique. So that is why we want some unique representation. So the reason why as to that definition kind of even remotely holds is because of distribution theory. We'll see why. And specifically distributions here. So we'll get into convolution. Has everyone seen convolution here? No?
No.
So
Say convolution. F star G.
F star.
Ah, yeah.
Everyone knows what convolution is? So just for the sake of definition of x is essentially integral this time over Rn f of x minus y g of y dy. That's it. This is what convolution is. Fine. Convolutions have nice properties. Everyone knows what the nice properties are. It's a kind of like a bilinear operator if you fix x, and well, yeah, those stuff. Derivative is the important part I will come to. If you take derivative, and one of these functions are smooth, you just need one of these functions. F star g. Let's assume f is the one we are talking about. This essentially comes out to be the derivative of f convoluted with g. That's it. This is the main thing that we even want to follow. Like, if one of these functions are smooth, then the derivative, then the convolution is smooth. This is the important result that we want. Your dad is worried about you. Oh, my dad.
Yeah.
What did it? Okay, sure. So this is how it is. Now, additionally, it follows linearity and all if you fix x. So that is a nice thing. So, anyways, this is as to say. Yeah, everyone's fine with convolutions, or do I need to prove this separately? The proof of this is not trivial, by the way. It requires something called dominated convergence theorem, but this holds. Fine? Yeah. So essentially convolution preserves derivatives, convolution preserves smoothness, it follows linearity. So I want to additionally also define if T is a distribution. I want to somehow define what this is. T star of G. So what I want is T star to be a function from d prime omega, from d of omega to d of omega. T was a operator from d of omega to r. It was a linear operator that was from d of omega to r. Now I want an operator from d of omega to d of omega. So
You're
how?
working with D again, not E. So you're
Now I
working-
am working with d. So how I define it is, first I have to make some symbols. So we'll come there in a minute. I have to first define translation, because if you see in our usual convolution, this will be essentially, we will formalize this concept by first formalizing TF of G, TF convoluted on G, and I want the result to be this. So I want, what I'm saying is, I want TF convolution G to be equal to F convolution G. This is what I want. So, being, what is it called? Inspired from this, I can define T convolution G in general. That is what I want to do. So now, notations, this is where things kind of get bad to see, because there are a lot of notations that come. I define tau x of G. It's again a function, so it's called translation function. Or I'll write y from d of omega to d of omega. This I define as, you take a function g and this operated as dy of g. And how is it defined? Ty of g, because it's a function, at x is defined as g operated at x minus 1. This is how I define. Now this is obviously an operator that is from d of omega to d of omega, because if g is smooth, this is also smooth. It's just translation itself. Then I also define reflection operator g cap in the same way as g of minus x. Fine. Now what I want to do is, I want to write f star g in the language of these two guys. Can you tell me a way to do that? In terms of TF and G, that is. It's just symbolics.
Integral of tau y of f times
Huh?
integral of tau y of f
Sure. We can do that. So integral of
tau y of tau y f
tau y of f at tau y. You want to do tau y? Okay.
x. Yeah, that is x one.
G of y dy. Sure. I mean, yeah. I think I kept the standard's quite low here. I want to do it such that I don't want the integral here. So essentially I want to describe it in terms of Tf, G cap and tau y.
Okay.
So this operated at y, let's say. Or x, if you want x, then x. So in terms of these people. I want to write this in terms of these people. So you for sure know Tf comes out. So you want to somehow, so this is a standard result. F convolution G is same as G convolution x. That's G convolution f. So you can take x minus y here as well. It's fine. So now try to do it. I'll write it again. F of y, G of x minus y. Again, symbolism. Tf tau y. You want to take tau y, okay. Tau y. I want tau x because you want to operate it at x. So remember, Tf is an operator from d of omega to r. So when you say x, you fix x and then operate it. It will be Tx operated on g. T of minus x, I think. I mean, okay, we'll go step by step. It's better. So this is Fy. What was tau y? So you subtract y. So essentially, I want to subtract x, but it's the same as. So tau minus x.
Tau x G cap y.
I mean, I want to take x out, not y. If I take y out, then well, the integral is still there. I don't want the integral. So this is the same as tau minus x of g of minus y. But g of minus y is essentially g cap of y. Fine? And now this is essentially equal to Tf of translation by minus x of g cap. I defined convolution using these mumbo jumbo, and now I don't have a separate term like integral or anything, but now this is in terms of distribution. So I defined this as Tf operated on G. This makes sense, right? This is just, you're defining this to be equal to this. So now that this holds here, I can just essentially define convolution of distribution with a function as T convolution phi is equal to, you take the same thing but remove it. T operated on tau minus x of phi cap or reverse cap, I don't know. So when you say x, you have to also say operated at x. This is how I define it. So now the best question you can ask here is, because of the fact that that is, here you knew that this preserves differentiability. Derivatives worked nice. What about this now? Is this a function from? So what I originally wanted was the convolution wanted to we wanted to be a function from d of omega to d of omega. Now we don't. Now we know it's a function of x, but we don't know the smoothness of it. We don't know if it's smooth. So now we check the smoothness. So here I will do the proof. To check the smoothness with respect to any derivative, you fix one derivative. So take dou I. dou by dou x, yeah, that is of t star phi at x. I claim that this is equal to, so this is, let's say here, this is equal to t operated on dou I phi at x. Now, because of the fact that we are taking derivative of a distribution now, to make sense of that, you need to define what derivative of a distribution is. Now, in usual terms, if you had removed this x term, x minus one term, if you had taken a derivative, now this is bad to say that the derivative just comes inside, but believe me, it does. For people there, it is because of dominated convergence theorem. It's a very, very useful theorem in math, so that is why I say it a lot of times, but the derivative comes inside because of that. And well, if one of these functions are smooth, you can differentiate it. So essentially motivated by that, you define derivative of a distribution. So d alpha of t operated at phi is defined as minus 1 to the power. When I say mod of alpha, it's essentially you, so remember the multi-index, alpha 1, alpha 2, alpha 3, you add them up to the power this times t of d alpha phi. Why I said this is motivated from, you put this here, not here, instead tf of g, integral fg. When you take derivative, you essentially do integration by parts, right? So you do integration by parts again and again. So if you take d alpha of this thing, you essentially get this to be equal to minus 1 to the power mod alpha, and if let's say f was smooth, you get d alpha of f. This is a standard result from, so this is integration by parts in Rn. If you don't get Rn, take it in R. You don't get the rest of the terms because of the reason that G is a function with compact support. So at the boundary it's 0. So that is why you don't get the boundary term. And this holds in Rn as well. I wouldn't go to the actual form in Rn, but it's close to the same. And well, the thing kind of holds. So that is why you define it using this, and this is a well-defined definition. And well, again you can go into this whole proving the part that if t is a distribution, d alpha of t is also a distribution, because by definition, if phi n goes to 0, because of the fact that phi n goes to 0, phi any derivative also goes to 0, so d alpha of phi also goes to 0. So that is why this is how we define it. So now you can go to the proof of this. So proof of this. So we go by the limit definition. We are essentially taking limit. So first of all, we'll see what this is equal to. This is essentially equal to t of tau minus x dou I of phi cap, right? So now I want to take the dou I out. Now because how does dou I work? Derivative of a function, then you take minus 1, right? So what is the relation between this thing and dou I times what? What do I multiply? I essentially want to take the derivative out. Any guesses? Simple derivative. कुछ तो बोलो. It's just minus, no? It's minus dou I of phi inverse, because essentially phi inverse is phi of minus y. Derivative of that will take a minus outside. So essentially this thing is equal to this. So you get the fact that this is equal to t of tau minus x. So because t is a linear operator, this doesn't care about minus. You get this. You have derivative outside and phi cap. This thing is treated as a constant by dou I. Because so essentially if you take this tau y of phi, derivative of this with respect to x, in function language this is just dou I of phi of x minus y. So this is equal to derivative of this, which is essentially to say derivative of this evaluated at x minus y. I was taking derivative with respect to x. That is why, so no minus. So the derivative doesn't care about this term. So this essentially comes out to be minus t dou I of tau minus x phi tilde. And well, this is equal to, you put this term outside now because by definition, so this is minus dou I t of tau minus x, and well, you put the definition, so this is equal to dou I t convolution phi. Fine. Now the other result, to come from here to here, it's pretty easy. Why? Put limit definition. Limit as h goes to 0. You get linear terms. Phi of x plus h and phi of x term. What you do is, you essentially combine them inside t because t is linear. Now you can take the limit inside t. Why? Because if the inside term goes to 0, then outside term also goes to 0 by our continuity. So you can take the limit inside, and because you can take the limit inside, now it just becomes derivative of phi. So that is why it essentially matches with this part. And this is an additional result, technically speaking. So you didn't require all of this to prove this, but now you know that this is equal to this as well. So it's a good result to have. That's it. So yeah, this is how I define convolution, and you can clearly see that convolution of a distribution with a function is operator from d omega to d omega because smoothness is preserved. So nice thing. This is now where things get interesting. You can now prove that any distribution with compact support can be approximated using functions, distributions generated by functions. And how do you do that? For example, I'll take example because the general result is quite general to prove, but it is actually, well, the existence of such functions is what is harder to prove, but nonetheless, it's actually more or less similar. In fact, it's actually similar. The proof requires a bit of machinery. If you take Dirac-Delta, the reason why I has to say that thing is important, you convolute it with rho epsilon. This thing is a function in d omega. Fine? Everyone fine with that? I claim that t of this distribution converges to delta. Now what do I say by delta? This is called so in functional analysis terms, this is called convergence by a weak star topology, and in Saral Bhasha, it's essentially t delta star of rho epsilon of any function phi goes to delta of phi for all phi belonging to d omega. That is it. This is what it means. So now you can check this easily because now it's just integral. This operated on this thing. What is it? It's 1. So this is just integral phi. Integral phi, what is the neighborhood on which this is defined? It's a ball of epsilon radius. Ball of radius epsilon around 0. This goes to phi of epsilon. Essentially to say, I mean, am I missing something here? Phi of 0. I think this might not be true. T of delta convolution phi epsilon. You get additional terms as well. So you get some constant c omega. That's why c omega was important. So essentially you get c omega, or rather, in fact, the volume of the ball, or rather 1 over the volume of the ball. Because what was this? Right. That's why it was getting. At 0, the value of this is still 1. So whatever you are left with is c omega, c epsilon. C epsilon in fact is equal to, in the beginning as I said, it's equal to 1 over the volume of the ball of radius epsilon. So you get volume of ball of radius epsilon. And if you know anything about integration, if phi is Riemann integrable, this is essentially the average integral of phi over the ball. And if the ball decreases in size, it essentially goes to the valuation of the function at that point. And hence, you can see that this is true, this holds. But if you see what delta star rho epsilon is, what is delta star rho epsilon? It is essentially delta operated on, definition, tau minus x of rho epsilon tilde. Fine. Rho epsilon tilde is the same as rho epsilon because minus x. This is essentially rho epsilon of, if you operate it at y, it's essentially at y, so it's essentially delta of, this wouldn't make sense, but just to give the reason as to see what it is, this inside terms become y minus x. Fine. You operate it at y equal to 0. Hence, this becomes rho epsilon of minus x. Again, rho epsilon of minus x is equal to rho epsilon of x. You get form functions with increasing radius because volume goes to 0. Volume of this thing, ball goes to 0. So 1 over the volume is essentially kind of going infinity, right? 1 over the volume goes to infinity. So essentially, what I see is, you approximate Dirac-Delta in physicist term. No offense to the physicists, but this has been said a lot of times in physics classes. So, like, it essentially goes like this. Our original idea, or the nonsensical idea, matches with the theory in place. This formalizes the concept of Dirac-Delta. So the integral definition matches with this, and reason as to why you can approximate it with Gaussians is just one more step. You have bump functions now. Do the same with the convolution with Gaussian. It follows to the same steps, and you get the same thing, and hence the reason why it gives the same value, and that is why Dirac-Delta is such a thing. And now, how to solve? So this will be the last part. There is a small part of it with Fourier transforms, but I don't want to go there because then we will have to define what I call Schwartz space and all. But I'll just give an idea of what it is in the conclusion, that's it. Rather than defining exactly what it is. What was I doing again? Green's method. So Green's function. The derivative and all written in a linear operator way, operated on f gives you g. What I try to solve is L of a distribution E gives you Dirac-Delta. How do you solve this? Take any function phi. Phi of 0. This is the equation I have to solve. This is much more easier than you think now, because now this is just a distribution. You take, these are derivative terms. Derivative of a distribution is essentially some constant, that is -1 to the power alpha, whatever, mod alpha, and you take derivative of phi inside. This is equal to phi of 0. Much more easier thing to solve, because now it's a constant outside. This thing you can solve, you get E. My required F is essentially E convolution G. Reason as to why. Apply this here. It's essentially delta function convolution G. But what is delta function convolution G? It's just G. Hence, you formalize the concept of Green's function. This E is in fact called the Green's function, which is technically not a function and it's a distribution. There is somehow a way to further show that E in fact kind of can be also approximated using functions, but that's separate thing. There is another nice result which I won't prove because it goes way too into technicalities. If T is any distribution with compact support of, like compact support same as Dirac-Delta, T can be shown as sum of some finitely many terms, okay, some coefficients A alpha, D alpha delta. This is a nice result that you guys can prove using function analysis concept, but it might be a bit technical. It is a very long proof, but it is a nice proof. There is another way to prove it using the thing I was saying called what is the order of the distribution and all. But nonetheless, it's a very nice result, and in fact, it's a quite general result. You can prove that if T is a distribution with compact support, it can be, and it has some nice properties, it can be shown as sum of other distributions with compact support. So the whole reason as to why this is kind of nice is, well, you are guaranteed that it's sum of some Dirac-Deltas or derivatives of Dirac-Deltas. By the way, first derivative of Dirac-Delta is called the dipole distribution, which is quite relevant in physics apparently. So yeah, that is Green's function. I'll just touch upon what is called what is it called? Fourier transform. You have to restrict your space technically speaking, but if you take it heuristically, Fourier transform of a distribution operated on phi, I define it literally as T of the Fourier transform of phi, or something along these terms. I am not sure if I'm right. I have to see the well-definedness and all, but the point is the Fourier transform kind of acts nicely with the distributions is what, and you can prove that this is true, and essentially this kind of becomes so the space of functions on which you can do it sits between D and E. So using the inequality or subset relation, you essentially get E prime inside S prime inside D prime. So inside these you can operate this, and you get this nice relation that Fourier transform kind of goes inside, and it in fact defines so Fourier transform, I should say technically distributional Fourier transform, and this is your normal Fourier transform. Distributional Fourier transform is a homeomorphism for topology guys, an isomorphism or a bijection between S dash to S dash. The result kind of comes because of the fact that Fourier transform itself is a bijection or homeomorphism between S to S. What is S? Space of some special functions. They are called fast decreasing functions. Essentially, as you go to infinity, they die down very fast. In general, the definition is just this. It's not that hard. It's essentially as x goes to infinity, x to the power any beta times derivative of any order of f mod goes to 0. very strong condition. Now you might say, is 0 the only thing that kind of follows this? No. You take this function 1 plus mod x square to the power 1 by p or 2p. So these kind of also follow. You take any derivative and you multiply it with anything, it kind of also goes to 0. So that is why these are nice functions. You have other functions. So here I have to, this is defined for all r. So it's nice, it's fine. So in fact, this space was first characterized using this. So there is a relation between when a function follows this, and if and only if relation between when a function follows this and when a function f multiplied by some term of this kind also follows this. That kind of relation. But nonetheless, we will not go there. That will take too much time. But yeah, Fourier transforms perform nice with distributions. This is one thing I wanted to touch upon. Another, I guess, in 5 minutes we will conclude is why it kind of also is good to study in case of, let's say, something called Sobolev functions. We will not define what Sobolev functions are, but we will define weak derivative. G is said to be weak derivative of f if for all phi belonging to d omega, integral f phi dash, when I say phi dash, technically speaking, d phi or d alpha phi, where I will say that alpha mod equals 1. I am first defining alpha of order 1. So alpha 1, but well, I need to go, so I'll take r for just this case. You can define it for r and other, but just for this, you take this d f phi dash is equal to minus integral g phi. Do you see why kind of it resembles derivative? Or as to reason why I can call g as a weak derivative of f. Speak up.
Boundary conditions.
Integration per parts. It's
Boundary
essentially,
conditions aren't applicable.
it kind of resembles integration per parts. Assume f was smooth. If f was smooth, instead of g you will have df. You will not have boundary terms because it's 0. Phi is 0 at the boundary. But if f is not smooth, but there exists a function g such that this is true for all phi's, then I call d, it's the same notation in literature, I define this to be equal to g. This is called the weak derivative of g. This is not always true. I'll give you an example. Everyone knows what a Dirac-Delta function is? No, right? Okay. I'll take it. So it is a function which takes 0 on takes 1 on rationals and 0 on irrationals.
Okay.
Yeah. So if I take Dirichlet function, not d, I take this phi of x 0. Now I don't remember if it was 0 or 1 yet. I can get confused between them, but I'll use it according to my convenience.
0 and flash.
Huh?
0 and
No,
flash.
sorry. Zero derivative.
It doesn't matter, by the way. It's just a definition. Any way around, it's fine. I just want to call this function.
Because
Not
the-
irrationals.
Yeah, because the integration is 0. So
Ah, sure. But I want which one will be better here? If I call,
If it doesn't work, just take
Measure
1 minus
zero.
5 and call it.
Measure 0.
I mean, sure.
no, see.
Like there's a reason why I am doing it, so that's why. So anyways, you take this x belonging to, let's say, rationals,
No, he's like
Or
measure
irrationals.
0.
and 1 on rationals.
Integration
If I do this,
is okay.
what is integral of phi for any this thing? Yes. What is this equal to? Okay, when I say this, it kind of goes into the Lebesgue integral criteria, but nonetheless, what can you see it to be equal to? Speak up.
0.
It's 0. Why? Because it is a very. Have you heard the thing that there are only so many few rationals? Rationals are very small. So sure, measure of rationals is 0. So because of the measure of rationals is 0, integral over this is essentially similar to taking integral of 0 times phi dash. Because measure of rationals is 0. Won't go into the Vivek integration part now, that's too much. So anyways, this is 0. But this is essentially the same as integral of 0 times pi dx. So d phi is equal to 0. Even though literally it's not continuous even. It's not even continuous. Now this is a very trivial example, but you can do a very more complex examples where you can actually find functions which are not even almost continuous. This is something called almost continuous because, well, usually it's only in a small set it's not continuous, everywhere else it's continuous, so it's almost continuous. Now for a rigorous definition, it's continuous almost everywhere. I just literally said the same thing. Almost everywhere is an actual terminology by the way. So yeah, that is why this kind of holds, but in general there are functions which might not even be almost continuous but might have this kind of a derivative. So these are called weak derivatives, and when you apply some special kind of norms, you define spaces called Sobolev spaces. And you kind of see here, right, that if you take a function which has a weak derivative, it's essentially integral f phi dash is equal to minus integral g phi. Essentially to say, tf operated on phi dash is equal to minus tg of phi. So the whole point of this is analyzing weak derivatives is essentially to say, because I could have, what is in terms of derivative, what is derivative of tf? Derivative of tf is tf of phi was defined as minus tf of phi dash, and we are essentially solving for when dtf is equal to some tg. This is what we are essentially solving for. We didn't have to go through this route, but it's a fun concept. That's all. Using the convolution concept, by the way, you can also prove the fact that this is dense inside LP. I don't want to go into the LP part. We'll do with the continuous part. We'll show that this thing is dense inside continuous functions, set of all continuous functions. Any guess as to how you can do it?
What is the metric that you're using on continuous function? The square.
Huh? Point-wise.
Point-wise.
Everything point-wise. Well, essentially to say, I am saying I want to prove that this guy, C infinity, say CC, or rather in our notation, D of omega is dense in C. Essentially to say, for any f belonging to C omega, continuous functions, there exists fn belonging to d omega such that fn goes to f. This is what I mean. Anything?
D omega is just bump function.
D omega is not bomb function. It's I mean, yeah, sure, it's functions with complexity.
Same.
They're pimple functions. So it's actually quite easy. You just take fn to be equal to f star rho epsilon, and take epsilon kind of going to infinity, and you essentially get so rho 1 by n. So how you take 1 by epsilon or epsilon or not, that depends. So I might have kind of, maybe made the notation here bad, but you can fix the notation yourself. It kind of follows there. You will know what to do when you go back and realize, okay, where do I take 1 by n or n? So depending on that, you can change the notation. It's fine. But nonetheless, the point is this thing, and you can easily prove that this goes to f pointwise or uniformly. Does it go to f pointwise or uniformly?
At least pointwise.
It goes to f pointwise. So how you do it is, you take the usual definition, this minus f, and then you take the integral definition, you do the integration, and well, you take, so here, row of phi is anyways 1. So essentially you are doing this f star rho 1 by n minus f, and then you can take integral and take f outside, integral rho 1 by n. You do this, you do this condition on x minus y condition on f, you get continuity term times rho of 1 by n. How you do that afterwards? Because dominated conditions theorem. Okay. But nonetheless, the point is, you can bound one of these guys by epsilon because, well, it's just continuous, and the other term is bounded by 1. Right? It's a bump function. It literally has only one bump, and it's bounded by a value. So you can bound that. Rest of the terms are fine. So you can apply. So I am saying bounded convergence theorem a lot, so I can also tell this just the theorem, not the proof, as to why I am saying it after again and again. If fn is a sequence and fn goes to f pointwise, and fn is bounded, then integral fn goes to integral f. This is what bounded convergence theorem is. Dominated convergence, right? DCT. So be sure that if this condition is not applied, this is always not true. So yeah, this is the theorem I have been applying again and again. It's a pretty widely used theorem in the area of functional analysis. So what I've done today is a small part of what is called functional analysis or advanced functional analysis, which you see in many graduate studies, or if you take a special semester project, maybe you can see it. This was a very small part of my semester project. Further, we wanted to get into solving special kind of, so now it's just about my semester project. This was all done. After that, we essentially wanted to, so this was just so that we could go into something called solutions of elliptic PDEs. Elliptic PDEs, an example for you is Schrodinger's equation. Schrodinger's equation, even if you take, everyone knows Black-Scholes? There is a very famous equation in finance called Black-Scholes. So even though it's a stochastic equation, stochastic model, you can do some analysis using deterministic models. So if you take away the time independent term, it's a elliptic ODE. Then under some conditions, I think even Navier-Stokes kind of boils down to elliptic PDEs. I don't know. I am not really seeing that. But yeah, elliptic PDE is a very general concept. So solving those is, of course, a very pain in the ass because, well, you don't know if always the solution exists or not. So my whole project was about existence of solutions, and when you can say, or rather, when you say a PDE has a solution, it might not always have a solution in the derivative sense. It is always differentiable. That is why you get into this analysis of Sobolev spaces. You define weak derivatives, and you see when can this PDE can be solved in weak sense, in that the solution belongs to some kind of Sobolev space. But the whole project kind of began with me studying them using an even weaker analogy of a solution using inner products, because I don't know how many of you know what a Hilbert space is, but the Sobolev space of certain kinds are also Hilbert spaces. I think, certain kinds are also Hilbert spaces. So that is why we went into this whole aspect of proving when does, so now everyone knows what inner product is. When does an equation like, so let's say B is a bilinear operation, B of u comma v is equal to inner product in the space f comma v. Let's say if this holds for all v belonging to whatever our space H is, Hilbert space. This is a very general theorem. When does this have a unique solution? So under these two special conditions, it's called the Lax-Milgram theorem. This has a unique solution, u. Problem is you can't do this directly for at least for an elliptic equation. So you kind of get into this analysis of okay, constructing a bilinear operator that kind of follows this. You get a unique solution there. Then you get into this whole analysis of the eigenvalues of this bilinear operator. Now eigenvalue everyone is familiar, so I touched upon it. You go into the analysis of eigenvalues of that operator, and now there is a nice thing in functional analysis that eigenvalues kind of behave nice if your operator is of certain type. Specifically, it's called compact operator. Not the same as compact distribution; it's a separate thing. But nonetheless, if it's a compact operator, it has a nice thing about it, nice things about its eigenvalues and how they are separated and how they kind of diverge. So further analysis on that kind of also gives you an intuition onto how our elliptic PD is. You can either say that okay, it has a unique solution, or the solution to this is non-trivial. Either this, I should take XOR in this sense. XOR H equal to F. So either this has a unique solution or this has a non-trivial solution. Both of them can't be true together. Yeah.
Is the weak derivative unique?
The weak derivative, as I said, it's like this thing is not differentiable, but it's weak.
No, is the solution unique?
So when you define by this, the solution is not weak. You don't know. You know that the solution exists in a Sokolov space, but you wouldn't know if it is the solution in the PD sense that you can differentiate it using integration by parts. For that, you further go. This is called regularity of a solution. In math, regularity certain many times implies okay, when can you say something is good in a stronger sense? So now you have a very weak definition. So with this, you essentially get a unique solution under certain conditions. And when you have a unique solution, now you can say, okay, when is this stronger? In the sense, when is it actually weak? That is called some regularity conditions. You see when the coefficient. So if your operator, so an elliptic equation is essentially of this kind. So D alpha F A I J plus B I D F. So these are vectors, by the way, or these are matrices technically. This is a vector, so I'll say B plus what is it? Some C type vector. So I should write alpha. And under you put some conditions on A alpha as well. I won't go there. It's called uniformly convex blah 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 shit. But the point is, and also this is one form of writing an elliptic equation. You specifically do this for a divergence form as they are called. But in usual scenarios, in your Schrodinger equation everywhere, coefficients are usually differentiable, and that is why you can kind of interchange between the forms, and that is why you can apply this theorem. And you get this uniqueness of solution. Further, you see what are the nice conditions on these guys. You get weaker solutions, and once you have weaker solution, now you can think about when can you say this is actually a strong solution, right? This is actually differentiable. Then you get into this now this gets into very high advanced functional analysis. You get into actual Sokolov spaces territory. You have a lot of inequalities there. Believe me, when you learn PDs, you deal with a lot of inequalities. You will just get fed up. Point is, these inequalities kind of go into further proving continuities of the functions. Once you have continuity of the function, then you get into this whole territory of. So there is something called Lipschitz. Everyone knows what a Lipschitz is?
Lipschitz continuous?
Lipschitz continuous. So essentially, f is said to be Lipschitz if f of x minus f of y is bounded by some c times x minus 1. There's further something called Helder continuity where you put alpha here. Alpha is some constant. So you get into this whole point of defining when can you say these weak derivatives or these functions are whatever Helder continuous. And there is a nice theorem about these guys that if your function is Lipschitz, it's differentiable almost all the time. So where it's not differentiable is on a set like this, like rationals. Most of the time it's differentiable is the point. So it will be not differentiable maybe on the measure 0 set. Once you have that, that is exactly the solution you need. Because if it's differentiable, it's essentially strong differentiable. So you got a solution. When I say all of this, it seems pretty light, but it's a lot of work. Then you go into boundary regularities, blah blah blah, maximum principle, a lot of stuff. But the point is, whole goal of this is to see when a solution exists, uniqueness of it, and when does a solution exist in the strong sense. And though I would say you did not require a lot of distribution theory for this, having the knowledge of it tells you things about convolutions, and if you require something like, okay, you specifically need to solve a differentiable equation, when you get into, let's say, this Green's function and all, you specifically know when you can apply it and why you can apply it. That is why the whole distribution theory concept is important. And when you further get into it, you see some nice results, which I did not touch upon today because you'll require further knowledge of function analysis and measure theory for that. But yeah, I think that I hope so it was useful for you guys. If not, I don't know, you can ask me questions. Yeah, that's it. Thank you. Any questions? No questions? We can end it right now.
You ended it earlier this time.
Huh?
You ended it earlier this time.
Yeah.